Hello. In this unit, we're going to continue the discussion of deep graphical models, sometimes called energy-based models. And we're going to give an algorithm, a theorem that provides an algorithm for back propagating through this exponential sized softmax involved in these models. So let's start by reviewing where we were. So we're looking at a graphical model. The simplest example or a simple example is semantic segmentation. So we have an image. We think of the pixels in the image as nodes in a graph. Each pixel is connected via an edge to its neighboring pixels. And we're interested in labeling each pixel with a semantic label like person, car, tree, sky. So if we consider the general case, we've got a graph and we want to label each node of the graph with some category. And there's going to be exponentially many possible labelings of the whole graph with little local node labelings. So we're assuming a deep network. So what's happening is we're assuming that for each node and each label for that node, there's a score or an energy. And these are sometimes called the Unary Potentials. And this is a tensor that, given a node and a possible label for that node, gives a score. And that we're assuming that tensor is computed by a deep network. So here X would be an image, and a deep network is going to compute a score for each possible label of each possible pixel in the case of images. We also, for each edge in our graph, we're assuming there's a deep network that computes a tensor that provides a score for each edge and each pair of labels on the two nodes connected by that edge. So this is like a compatibility score between the two possible labels. To what extent are these two labels compatible with that edge? And in semantic labeling, this potential will say the two nodes connected by an edge, if they're nearby each other, are likely to have the same label. So having different labels will be disfavored. We want them to be the same label. Okay, so the score, so in these slides, I'm going to use calligraphic Y to mean the global labeling of all the nodes in the graph. So the score of a potential labeling of all the nodes in the graph is going to be the sum over nodes of the local, the unary potential at that node for that labeling of that node. So this is a node and the labeling assigned to that node. We get a unary potential summed over the nodes. We're also going to sum over the edges and get our binary potential. So we take the two labels, this global labeling assigns the two endpoints, and we look up the score for this compatibility score. And then we're going to define a probability distribution over the global labelings by doing a softmax over the global labelings. So this is our exponential softmax. And then our loss is just going to be minus log probability as defined by this exponential softmax of the gold label. So this is calligraphic Y. So that means this is labeling all the nodes of the network. And the problem we're facing is we've got our gold label for the whole graph. We want to back propagate through this exponential softmax to get the gradient attributes on these tensors. And once we can get the gradient attributes on these tensors, we can back propagate through these, just use standard back propagation to back propagate through these neural networks and update the neural network parameters. So our problem is the back propagation through this exponential softmax. Okay, so what the theorem that this unit is going to prove reduces this back propagation problem to an inference problem about graphical models. So graphical models were studied to death 10 years ago, and there are all kinds of inference algorithms for them, some of which provide effective approximations. The inference problem is fundamentally intractable. It's NP hard, but there are reasonably effective approximate algorithms or heuristic algorithms. So the theorem's going to say that to get the gradient attribute of this unary potential, that this gradient attribute is equal to a probability over drawing from this exponential softmax. Now, this exponential softmax, we can't actually draw from it, but the theorem's going to say that if you could, this gradient is for this node and this label for that node, the loss gradient with respect to this tensor entry is just the probability over drawing from the probability that we get this pair, that this node is assigned that label. And this is a probability over drawing from the model's probability distribution on global labelings. If this Y is the gold label, remember there is in training, there is a gold labeling of the whole global graph. If this Y is the value assigned by the gold label to that node, then we subtract 1. Okay, so this thing's easy to compute because we have the gold label. We know whether this is the gold label assigned to n. This is the inference problem. And this inference problem, as I said, is intractable, but we're going to look at algorithms for approximating it. And a similar thing holds for the gradient of the edge potentials. So it's the probability that when we draw from this distribution, the global labeling that we draw assigns this pair of labels to this edge, minus 1 if this pair of labels is the gold label. So now I'm going to prove this theorem. The theorem is going to say the backpropagation over the exponential softmax reduces to the inference problem for the graphical model. So let's look at, and I'm just going to do the unary potentials. So let's look at the gradient attribute for a given node and a given possible label for that node. So that's this gradient attribute is the partial derivative of the loss. This is the gold label, global labeling of the graph, of the partial derivative of this loss with respect to this particular tensor entry, right? That's where we want to get that. That's this grad value is the gradient of the loss with respect to this particular tensor entry. So I'm going to take the loss and just plug in its definition. So the loss is minus log the probability. The probability is a softmax, so it's 1 over z, the exponential of the gold label score. Okay, this is the standard probability. I'm going to take the derivative of that with respect to this one tensor entry. So I'm going to take this expression and separate the log z from the log of the exponential of this. So this becomes this. Now I'm going to differentiate this with respect to this single entry in this tensor. So the derivative of log z is just 1 over z times the derivative of z. The derivative of z is a sum over the global labelings y tilde, y hat, of this exponential. So I'm differentiating this with respect to this tensor entry. So that's just the sum of this times the derivative of the score. So I've written the derivative of the score with respect to this tensor entry. This is a derivative of the score of this thing we're summing over, y hat. We also have here the derivative of the gold score with respect to this model parameter. So this is what the line I just had. Note that if I take this 1 over z and push it inside that sum, I get 1 over z times the exponential, which is the probability, the softmax probability. So this becomes the sum over y hat of the model probability of y hat times this derivative. Now, the model probability, the score, this is the derivative of the score. The derivative of the score is just this sum. If this ny does not appear in this sum, the derivative is 0, right? If the score doesn't depend on this parameter, if n is not assigned this value, this parameter is not used in computing the score. If this n is assigned this value, then the derivative of the score is 1, because we're just adding that that value into this score. So this derivative is 1 if this global assignment assigns this lowercase value. So what we, and a similar observation holds over here. This is 1 if Y is the gold label. So what we get is an expectation over drawing the global label from the probability distribution of an indicator function. It's 1 if this global value assigns this value to the node n, and it's 0 otherwise. And a similar thing here. This expectation of an indicator function is just the probability that the indicator function is true. So what we've done is proved our theorem that this gradient attribute is just the probability, according to the model's distribution, of getting this label for that node. This gradient is just the probability, minus 1 in the case where this is the gold label. This gradient value is the probability that this edge is assigned this pair of values under the model probability, minus 1 if this is the gold label, gold labeling of this edge. So what we're going to do next is look at algorithms for doing this inference problem. We're trying to calculate these probabilities for a given graphical model. And we're going to go through a few units on algorithms for doing this. Thank you.